So, Hi everyone. My name is Sanya, and I'm working as a researcher at Carnegie Mellon University and at IIT BHU. I've worked as a researcher at the University of Texas at Austin and at NIT Patna. I was on the official documentation team for NumPy, and I am a Kaggle master. And I will be working this summer at Cincinnati's Children's Hospital Medical Center in the domain of medical imaging itself. I can't really read your chats, so I'll come back to any queries that you have towards the end of the session. Maybe if you have any queries in between, please use your microphone because I can't read your chats right now. Thank you. Anyways, so let me begin with the presentation finally. So, what is an image? If you take a look at this picture right over here, you can call it an image, right? But what is an image actually, or in literal terms? So any picture, any photograph, a visual representation of anything can be said to be an image in literal terms. But if you talk about it mathematically or computationally, then what actually is an image? So an image is nothing but a function. An image is a function of two spatial coordinates, that means x and y. So if you can write f of xy, it is said to be an image. If we're talking about three-dimensional images, there would be yet another component. There would be yet another spatial coordinate called z in it. So, anyways, an image is said to be a function of spatial coordinates. An image is also said to be a matrix, but we are going to delve into that interpretation a little later on, or when you start with the coding part. Anyways, so what is an image and what is a digital image? So when the values of your x and the y, when the values of your spatial coordinates and the value of the amplitude of the function f of x y is finite, when you get finite values for x, for y, and for the amplitude f, you can refer to that image and call it a digital image. So basically, in this entire session, the images that we are going to be referring to are going to be digital images itself. Biomedical image processing is basically the image processing of digital biomedical images itself. So types of images. So if you're going to the abstract root of image functions of image processing, images can be broadly classified into two categories: vector or raster. So right now both of these appear to be raster itself because of computational dependencies. But a vector image is one which, even after zooming, would not pixelate. So I hope you understand what is pixelate. Pixelate means, leads to a slight degradation in quality. If you zoom into this image, you would see that the quality keeps on worsening and worsening as you keep on zooming into the image, right? So this is the basic difference between a raster image and a vector image. This means that even if you zoom deeper into the image, a vector image won't pixelate. A raster image, however, once zoomed deeper, would pixelate, and the quality of the image would get down, would degrade faster. So the smallest independent unit of a raster image is called a pixel. Hence the term pixelate. So if you zoom deeper into a raster image, which I can't do right now because of PowerPoint, you would be able to make out the pixels or the building blocks of the image. Pixels are said to be building blocks of a raster image. We are going to be dealing with raster images itself right now. So types of digital images, like I said, types of raster images. So this is where the main fun part of digital images begins. So we have three different types of digital images when we are specifically talking about medical images. So first of all, you have binary images. Binary images are ones which have only two pixel values. You either have a 0 pixel value, which denotes the black color, or the 1 pixel value, which denotes the white color. So not to be racist, but 0 denotes black and 1 denotes white. These are binary images. Now these images, like as I said, only contain 2 pixel values, so they only contain two colors, maybe if you can call them colors, that is white and black. This is the image of a cerebrum, as you can make out. Anyways, next up, we have grayscale images. So what happens is that people usually get these two images vehemently confused, and it is not right because people usually called black and white images, which are binary images, that are 0 1 images, and they refer to when we're actually referring to grayscale images. So black and white images are not actually grayscale images. Black and white images are binary images. If you take a look at this particular grayscale radiograph image, this is the radiograph of a dental of a dental image. So it contains different levels of grays. All of these are grays itself, right? Because some grays are darker, some grays are lighter, but all of these are grays itself. So a typical grayscale image basically contains 256 gray levels, right? 256 gray levels are present in a grayscale image. Gray levels are nothing but the extent of the lightness or the brightness that we are going to be talking about. So, like I said, in binary images, 0 was supposed to denote black and 1 was supposed to denote white, right? But in the case of grayscale images, 0 still denotes black, but your white is denoted by 255. 256 is not it. There are 256 gray levels because we range from 0 to 255. So the gray level 255 is supposed to coincide with white. Let me just write it down if you are facing any difficulties. So 0 basically denotes black, and 1 in this case denotes white. And if you're talking about 255 in this case, then it denotes white. Okay. So there are 256 gray levels, as I told you. And in an entire grayscale image, there are supposed to be multiple pixels, and each pixel is said to contain 8 bits of data. Fine, there are 256 gray levels, and each pixel contains 8 bits of data. So, this is basically the 8-bit per pixel encoding format of the image. This was the form of image that was predominantly used in Unix, in the Unix operating system. But now you have higher standards, higher orders of images. So typically grayscale images contain 8 bits per pixels. However, if you're dealing with some high quality medical images or some high quality astronomical images, then these pictures can contain 12 to 16 bits per pixels as well, right? So please don't get confused between gray levels and pixels. Pixels are going to be the independent values inside a picture, right? For example, if you envision this as building blocks, each of these blocks would be a pixel. Gray levels would just be the intensity of the pixel. How what is about it, which gives more information about the intensity of the light present in the given pixel, right? Pixels and gray levels are completely different things. Gray level is a property of a pixel. Okay, if you can talk about it in layman's terms, gray levels are properties of a pixel. Now, next up, we have colored images. So, uh, colored images, the most important and the most fundamental point about colored images is that they contain 3 channels. So, a grayscale image basically contains only 1 channel, right? But colored images contain 3 channels, which are known as RGB. Let me just change the color again. R, G, and B channels, red, green, and blue channels. Okay, and because each channel contains 8 bits per pixels, the total number of bits inside one pixel is going to be 24 bits. Right, this is the 24 bits per pixel format for colored images, for colored digital images. There is also another format of images, of colored images, called the 16 bits per pixels. So, as the name suggests, in this particular example, in the 24-bit images, in the 24-bit per pixel image quality value, you had basically 8 bits for each channel, right? So, the R channel contained 8 bits, the green channel contained 8 bits, and the blue channel also contained 8 bits. But if you're talking about the 16 bits per pixel picture demonstration, for this you had 5 bits for the R channel, 6 bits for the green channel, and 5 bits for the blue channel. So, why this preference towards green? This is because green is considered to be a relatively milder color than red or blue, and therefore it was given more preference so that it suits the eyes more. This was the first encoding format, the first color encoding format that was brought by Microsoft Windows, and it had the ability to display about 65,500 something colors. And However, this was evolved later on to the 24 bits per pixel image quality demonstration. I hope this was clear. If you have any doubts, please unmute your microphone right now and ask. If not, you can also ask towards the end of the session. So if you
Hi,
have any
Sanya.
doubts,
I'm Daud.
hi, hi, sure.
Hi. Is there any reasoning behind allocation of the number of bits per color channel?
So basically, it depends on picture quality value, about the extent of the quality that you would prefer to have in your images, and also it depends on your computational resources, because obviously it is considered to be very expensive while you're training colored images as well, because it demands a lot of GPU and it demands a lot of memory as well, right? So 24 bits per pixels is considered to be a standard value that was used by researchers, that was used by software companies in the beginning, and that is the trend that has been continued on. And nowadays also colored images contain 24 bits per pixels itself, or 16 bits per pixels, whatever suits them.
Okay, sure. Thanks.
Thank you. Any more doubts? Okay, so I'll just proceed to the next slide. I hope this was clear. If you have any doubts, please ping me. So, what is image processing? So, digital image processing basically means processing a digital image by means of a digital computer to extract some useful information. So, if you're familiar with something called signal processing, digital image processing is just an abstraction of it. It is a small part of it. So, usually, signal processing is divided into two types. You have speech processing and image processing. Image processing is supposed to deal with processing input images to yield output images. So I found this really interesting diagram on Geeks for Geeks, and I decided that I should present it in this session. So when the input of a given algorithm is an image, and the output of a particular experimentation of that particular experimentation is also an image, then it is considered to be digital image processing. Fine. So when the input is an image and the output is also an image, it is considered to be digital image processing. However, when you have an image input, an image based input, and the output is not an image but a description, now this description could be something about the image, or it could also be some parametric quantities, right? For example, uh, let us imagine that I fed an image of a brain into an algorithm, right? Now, once I fed the picture of a brain into my algorithm, and my output was this is the picture of the cerebrum of a brain which suffers from, let's just say, glioma tumor. So, this was a particular explanation, this was a description that the algorithm provided to me as a result of its functionality, right? So, when we are feeding an image into an algorithm and the reply, the outcome is a description, that particular part, that particular abstraction of it is called computer vision. Fine. Because people often tend to get image processing confused with computer vision. They are very, very close. In fact, it is also said that computer vision is a small part of an image processing. However, they are not the exact same things. So keep it in mind. Next up, if your input is a description, for example, if I want to say I want a helical three-dimensional structure, and your output is a graphic that supports my description. For example, if I wanted to say that, okay, I want, like I said, a three-dimensional helical structure, and my output was a graphical demonstration, a graphical representation of the helical three-dimensional structure, then that particular branch, that particular operation would be considered to be a computer graphics operation, right? Because I supplemented my needs, I supplemented what I want in the image, and appropriate images were modeled as a result of my description. So, this is an example of a computer graphics operation. Next, if you feed the description of an image into a particular operation, sorry, and the output of the particular processing is also a description. For example, if I said that I want a brain image, right? You will be getting brain images, you will be getting quantities associated with the brain image. For example, a better example for this could be, let's just say that I'm running an algorithm to identify the type of brain tumor. Fine. So I entered information about the type of brain tumor, I entered the features which I want my model to be trained on, and finally, once your model has been trained, your algorithm will be able to identify what sort of tumor is present in what image, right? It will be able to tell you this is glioma tumor, this is meningioma tumor, this is pituitary tumor, this image is free from tumors. So your input is also basically a description, and your output is also going to be a description of the class of the tumor. So this particular operation is encompassed into artificial intelligence. So I hope the differences between these four niches, these four domains was clear to you. If you have any confusions, you can ask, or you can ask them towards the end of the session as well. Sorry. Next up, we have phases of image processing. So you can't just process an image in just one step, because there are numerous operations that you provide in order to render an image in a format that you would like it to be in, right? So there are a number of phases. Research is being done on all of these phases, some more than the others, and we are going to be talking about these phases now. So if you're talking about image acquisition, so image acquisition is basically rendering an image available for use. That this means that you can scale your image, you can convert it into different color spaces. There are different color spaces available, by the way. It depends on what your demand is. For example, we were only dealing with the RGB color space. A little later on, I'll tell you about the lab color space. It is just in this particular PPT, so stay tuned for that. So we have image acquisition. This means creating, rendering an image useful for our pipeline, whatever pipeline is that you're using, whether you want it for detection of a disease, whether you want it for segmenting particular anatomical features in an image, in a medical image, or so on. Image acquisition is basically acquiring the image and converting it into a format that could be used by you further. Fine. Next up, we have image enhancement. So, image enhancement is by far the most fundamentally worked on domain of image processing. A lot of work is being done on image enhancement. Image enhancement basically means rendering an image useful for further use. What if I click an image in low light and I want to use that image in the detection pipeline to diagnose a particular disease? If the particular image is low quality, it was clicked in poor lighting, not even the doctors, nor the machines, nor the computer aided diagnosis software would be able to diagnose the disease or detect the traces of a particular abnormality in it, right? Therefore, it is very important to enhance the quality of the image and then put it into the detection pipeline, put it into the segmentation pipeline, and then get the acquired results. So, image enhancement is one of the most fundamentally worked on domains of image processing. Next up, you have image restoration. You performed a number of operations on your image, which resulted in quality degradation. Now you want to get back, you want to restore the original quality of the image, and that is when image restoration steps in. These are steps that are basically used to bring the quality of the image back to its original format. Next, we have color processing. So, color image processing or color processing basically talks about processing the colors in an image, like I said, converting into multiple color spaces, handling the contrast, handling the color of the image, and so on. Next, you have multi-resolution processing. Multi-resolution processing means that you can process your image on multiple grades, on different levels of resolution. For example, you have different formats, different methods to format h to process HD images. You have different formats to process TIFF images. You have different formats to process your regular JPG or PNG format images, right? So this is called multi-resolution processing. You can process images belonging to different resolutions, different having different levels of clarity and having different formats as well. Next, image compression. We use a lot of image compression softwares these days, especially available on the internet, to compress the size of the image. Because usually, like I told you, colored images take up a lot of memory and they take up a lot of computational resources as well. So sometimes you need to compress the size of the image in order to dispatch it or to send it somewhere. So image compression is therefore useful here. Next up, we have segmentation and detection. Segmentation basically refers to demarcating or describing and segmenting, or basically describing the outlines of a given anatomical feature, of any given feature, by the way, and basically making its boundaries clear. So once, for example, if you are working on something like diabetic retinopathy detection, fine. So if you, I'll come to that also later on. If you're working on diabetic retinopathy detection, you can actually make out the presence of the disease if you take a close look at the vascular segmentation, if you take a close look at the network of veins present in the image. But how do you take a look at the network of veins? Let me just show you this particular image. Yeah, this image that you see right here. So it's often, blended with a lot of other artifacts present in this image. For example, you have a little bit of noise right over here. You have the macula right over here, which is causing a lot of light. So you can't exactly make out the network of veins here, right? That is where segmentation algorithms step in. This is where you can see just the network of veins minus the external environment, minus the external features. This will help you to diagnose your diseases further. Once you have segmented your images perfectly, you can then run it in a detection pipeline and finally diagnose the presence of a disease. Or if you're not working on biomedical, I was just talking about it in a biomedical time frame, you can detect the presence, or you can recognize images, you can classify whatever it is that you want to detect or classify in your sample image. So I hope the phases of image processing were also clear to you. So I'll come to all doubts towards the end of the session, so don't worry about that. Uses of image processing in the biomedical domain. This was the vessel segmentation example that I was talking to you about. You can actually see the reticulation of veins right over here. You can actually see the network of the main veins followed by the different nerves that are present over there. So this is how you can predict the presence of a particular disease or not. So uses of image processing in the biomedical domain, for example, in tumor detection. I gave you the example of tumors. There are multiple other diseases that could be detected using biomedical image processing. There are a number of scans that are conducted every day, like CT scans, MRI scans. Histopathology images are used to detect the presence of multiple diseases. Then you have ultrasounds that are conducted to detect the presence of multiple diseases. You also have dermoscopies that are conducted. So all of these are imaging techniques, and once you can analyze these imaging techniques, it will help you to gain a broader idea or gain broader insights about whatever is going on in the human body, and then finally gain some concrete insights that you can process and then use them accordingly. So tumor detection was one example. Segmentation I already talked about. Then you have region identification. You can take a look at this particular image right over here. It actually demarcates the different regions of the lungs, which is actually a very well trained algorithm because it's actually being able to identify even the smallest of the nodules present in your lungs. So, this is how resolute biomedical imaging is, how resilient it is, and how well can it segment the different domains of an organ of any part of the human body, and therefore aids in the detection pipeline. Now, what is a good medical image? I have been talking about the use of images. I have been talking about why our image is important. But how do you call an image good? Because when you look at an image, when you look at a picture of yourself, you consider how well do you look. You consider how your background is looking like. But when you're talking about a medical image, you don't care about if the particular organ is looking fat, if your particular features are not as good as it is supposed to be. You just care about a fixed number of factors that would contribute to the prevalence or the presence of a particular disease in the image or not, right? And to ensure that you are able to make out the disease present in it, there are a number of resolutions, there are a number of standards that your image must adhere to be called a good medical image. So first of all, it should be natural, because what happens as a result of multiple enhancement algorithms is that your image loses its inherent naturality. We don't want that to happen, because at the end of the day it is only an image of a body part. It is not supposed to have extreme brightness, extreme contrast, or a lot of saturation. It is supposed to look natural. Next up, well illuminated. This means that low light images should not be considered for the detection pipeline or for the detection landscape. Your images should be well illuminated. If they are not well illuminated, you need to run an appropriate enhancement algorithm on them to improve the quality of your image. Next, anatomical feature visibility. There are multiple features. For example, I was talking about diabetic retinopathy. The image that I showed you was that of a retinal fundus. Retinal fundus is basically the part of your retina that lies behind your eyes, right? So you can't literally see it. However, there are fundoscopes and fundus cameras that are used to click those images. Fine. So There are multiple organs, there are multiple parts present inside your retinal fundus. There is the macula, there is the optic disc, there are multiple veins. Like I showed you, there was an entire reticulation of veins. There are lesions, so there are hemorrhages, and it is very important to actually detect the presence and to detect the boundaries of these features, right? So only if you could detect the presence and detect the boundaries of these features would you be able to find out, and would you be able to grade the quality, would you be able to grade the quality of the image, and you would be able to grade the severity of the disease as well. Because obviously, if you are not able to find out, if you're not able to make out that a lesion is big or not, if a lesion was big but you couldn't be able to, you wouldn't be able to identify the reason to be big or small, then it would lead to an aberration in the detection pipeline. It would lead to an error in the detection landscape, and your disease would not be able to get diagnosed immediately. Next, we have segmentation. Like I said, anatomical feature visibility ultimately is a consequence of clear segmentation as well. If you are able to segment out the body part, segment out the anomalies and the artifacts in your image clearly, then you would be able to have a good quality image. Preserved brightness. Images with a lot of brightness or with poor contrast are not considered to be good quality images. Your images need to have uh, a fixed resolution. They need to be natural, because unnatural images have uncontrolled brightness. So your brightness should be preserved and your contrast should be enhanced. So let me just show you what a good quality image is. So this was the image of a benign melanocytic nevus. Melanocytic nevus is basically something like a mole on your skin. So this is what I got from the ISIC archives. You can also fetch this data set. It contains, I think, 800 images, 800 benign images, and 800 malignant images as well. So you can take a look at this particular sample picture. So this appears a little blurred. The reticulation of veins is not present, as well as the center region, the center cortex is not very visible as well. However, once you run an image enhancement algorithm on it, we are going to be running this image enhancement algorithm right now as well. So you can take a look at how well this the skin can now be perceived. You can take a look at the reticulation of nerves, you can the reticulation of veins right over here. You can also clearly demarcate its boundaries. So this is actually a good quality image. Now let me just show you how can you enhance raw images into a quality that you would like it to be in. Fine. So there are a number of image enhancement techniques. You have filtering techniques. So filtering techniques are basically neighborhood operations. This means that since any image is construed of multiple pixels, you are not going to perform an operation on a particular pixel. You are supposed to be performing operations on the neighborhood of a particular pixel. Fine. So because every pixel is ultimately inside the neighborhood of another pixel, you're ultimately going to be working on all the pixels indirectly. So there are multiple filtering techniques out there. For example, there is median filtering, Gaussian filtering, Wiener filtering, and all of these different filtering techniques are ultimately used for denoising images to remove noise and artifacts from the image. Next up, you have histogram equalization. Histogram equalization is a very important contrast enhancement technique. So basically, every image can be represented as a histogram based on its gray levels, based on the intensities of its various gray levels. Fine. So once you are able to depict it in that way, once you are able to find out the intensities pertaining to each gray level, you would be able to make out the contrast and the brightness of the image. So usually if an image has a lot of values, a lot of gray levels pertaining to one particular spectrum of the histogram, I will come to that later on when I show you the image, it is not considered to be a good quality image. Throughout the range, throughout the x-axis of your histogram, you want your colors, you want your histograms to be spread out throughout the x-axis of your histogram, right? So that is considered to be a good quality, a good contrasted image. And henceforth, in order to obtain results like that, you have histogram equalization. I will get to histogram equalization just in a minute. Before that, we have contrast limited adaptive histogram equalization. This is an enhanced version of histogram equalization, which is specifically catering towards limiting the contrast, inhabiting the contrast, and to making the process a little more dynamic by taking in point of view, taking into perspective the neighborhood of the pixel values that we are going to be improving. Contrast limited adaptive histogram equalization was a groundbreaking technique, but it was introduced in the 1990s. So after that, a lot of work has been done to work on image enhancement techniques. A lot of deep learning based techniques have also come up. For example, you have zero DCE, you have MIR net. So all of these different deep learning based techniques were also developed to enhance the quality of your images. So uh, let me just start and give you a very brief workaround of what we are going to be doing. Just 1 second. Yeah. So what we are going to be doing is we have a sample image. We have a sample image of a malignant melanocytic nevi, and we are going to be enhancing its quality into this, because as you can see, this image is very very blurred. Its quality is very very poor, and you have to increase its contrast, its brightness, and its clarity by using a contrast limited adaptive histogram equalization, or the Clahe technique. Fine. So I would suggest you to have some very basic hands-on practice with MATLAB for image processing, because MATLAB is the sought after software for working on image processing. But since all of us, most of us are familiar with Python, I'm going to be working on this demo in Python itself. But for image enhancement tasks specifically, I think MATLAB has a greater edge over Python. Anyways, so the Python package that we're going to be using is CV2 OpenCV, if you are familiar with it. So first of all, importing the important libraries. This is just a system dependency. You can ignore it. Next, we have cv2.imread. I'm reading this particular image right over here. So if you're not familiar with Google Colab, you just need to click on these three dots and click on copy path before you actually feed this path right into it. Now, like I told you, there are multiple color spaces available right over here. Any image that you enter is typically in the RGB or the BGR. It's called BGR, in the BGR color space. But BGR color space is a little computationally expensive to work on. It's a little slow also to process. So what we do is that we convert our BGR color space into the LAB, or the lab color space. So the lab color space basically has an external component, an external contribution for lightness. The L in the lab stands for lightness, and A and B just refer to the pixel values of your A refers to the pixel values for the red and the green channels, and B refers to the pixel values for just the blue channel. So now we are creating this variable lab, and inside it we are converting the this particular images color space from BGR to LAB. Fine. Now we are going to be splitting this particular image lab into three channels, right? You always have three channels. Instead of B, G, and R, we are going to have L, A, and B. I'm just going to name it L channel, then A, and then B. And now I've split the sample image into these three channels. Now, you can apply CLI to all the three channels, but usually it is considered best practice to convert it to just one channel. So now I'm going to be using CLI. There's an inbuilt function in CV2 called create CLI, and these are just specific parameters that I got from research. You can also tweak these parameters as per your convenience. It's not an issue. Once you have run CLI, you can apply this particular function. You can apply CLI to the channel of your choice, that is the L channel. Fine. So CLI.apply is used to apply CLI. CLI was the function that was used to create CLI, and you can apply it to the L channel. Now, once you have applied CLI to the L channel, you are now going to merge this L channel with the other two channels that were available, right? You are now going to merge your new L channel. Your new L channel is called CL, right? You're going to merge CL with A and with B. So now you have a new image, that is LIMG, and you have created this by merging your new L channel, that is CL, with A and B. And now you can just take a look at your output image. This is just going to output the image. I've just used this particular variable to represent the enhanced image, and now I'm printing this using conversion into the lateral color space again. So now in order to print it, I'm finally converting the it from the lab color space to the BGR color space again, so as to view it in a better format. And now you can take a look at the output image. It is way more clear and way more discrete as compared to the former image, and the segmentation as well as the features are also very clearly visible as well. Now, if you want to take a look at the histogram for the first image, right, you can see that mostly the histograms are located after the 100th gray level and between 250. So this means there are mostly images on the lighter spectrum. But if I want to perform histogram equalization, on the latter image, you can see that the histogram for this is spread out right over from 50 to 250. So it has a much broader domain, it has a much more dynamic domain when you compare it with its counterpart. So basically, I want you to try this particular experimentation out on your own. If you have any doubts, I will share this code with you right after the end of the session. You can refer to it as well. And this is all I wanted to talk to you about when it comes to biomedical image processing. I hope I was clear. I am open to any queries that you have.
Hi. Could we please have the stack of slides also as reference in addition to
Sure,
the Jupyter notebook?
sure. No problem.
Yeah. Where could we find it? Will that be put up in the chat box right there?
Basically, we'll send it to you later on the Slack channel. Are you available on the Slack channel?
No, no. I'll join. I'll make it a point to join.
Sure, we'll send it there.
Or
Okay.
it'll be of great help if you could even like zip it and maybe send it to us just like the invites had been sent. The similar fashion, you can maybe send this over as well.
Okay, I'll talk to the coordinators about it and I'll let
Yeah,
you know.
sure. Thank you so much.
Thank you.
For people who are not on the Slack channel, I'll just be putting the invite link here so you could join.
Thank you so much.
Yeah, sure.
Sanya, I had a question.
Yeah, sure.
Like for someone who's starting out in biomedical image processing,
Yeah,
there are multiple ways to get started. Like there's brain tumor detection and many tumor detection or diabetic
yeah.
detection using eye images. So, like, where should one start out? Like, there are multitudes of researches going on in different detection or segmentation or whatever it is. So, for
Yeah.
someone who's starting out, like, what would you think is the right way to go ahead?
So that's actually a very subjective question. It basically depends on your perspective and what you prefer. What particular medical domain would you like to work on? Whatever suits your interests best. For me, or however, because most of these are focused on deep learning, right? Because usually we work on detection, we work on classification of medical images. My first work was malaria detection. Why was it my first work? Because you usually have multiple classes that you need to classify your images into, right? For example, if you're working on brain tumor, you have multiple types of tumors. You can classify into pituitary tumor, glioma tumor, meningioma tumor, as well as no tumor images, right? However, when it comes to malaria, you have only two classes. It's either parasitized or it's uninfected, right?
Right, right.
Therefore, it's always preferable to work on smaller problem statements once, and then you can expand to larger problem statements.
Okay, okay. Thank you.
Thank you.
Also, a little follow up to that. I'm also somebody who's just starting out.
Yeah,
So, is there a course that we could, like begin with? Because you mentioned to us that there are so many different image processing techniques, especially like, for example, enhancement techniques. You mentioned filtering amongst
yeah,
several
yeah,
others.
yeah,
So, I mean, it's a lot of information to, like
yeah,
grasp just within an hour or two, maybe.
yeah,
Because
yeah,
I've been looking up Coursera, for instance, and I've not found. Courses, at least with medical image processing, it's extremely difficult actually.
yeah, yeah.
So if you could just put some resources for us, some books, maybe some cookbooks or some links or anything, that'll be of great help, especially along the uh, Python front, like yeah,
Got it.
not just MATLAB, that too. Yeah, and because at the end of the day, I'm a deep learning researcher, so I'd work on classification and clustering kind of problems, so that'll be of great help.
Got it. So when I was getting started with image processing, I basically worked at a lab. So I got access to a lot of resources that they used to have. I feel like if you are somebody working on Python in the medical domain, there is a YouTube channel called Digital Srini. So he's like very good with it. I've put down the name in the chat box. I can also send you the link. Just 1 second. I'll just Google him. So he basically works on a lot of segmentation detection as well as enhancement problems. pertaining to the medical domain as well. So if you're somebody interested in biomedical imaging or in microbiology, computational biology, then he's your guy. You can definitely look him up. And he also puts all of his codes in the description box. So if you ever have any doubt, you can definitely refer to that. So I think it's a very, very good resource. It's a free resource. You don't need to look for any courses, any additional courses available on Coursera, because yeah, I know there are very little courses specifically devoted towards medical imaging. So don't worry, this is a very good resource, and I definitely say that it's a good place to start with.
Okay. Addition to that, if we'd like to go deeper into it, because I've done my masters,
Yeah,
and then I will be going on to do a PhD,
yeah,
especially in biomedical image processing,
yeah.
because that's something that I'm keenly interested in. So, if I'd like to dive deeper, are there some other resources, maybe like again, a comprehensive set that will basically give me everything that I need, or
So
at least 80% of what is out there? Oh, like.
Got it, got it. So, because biomedical is a domain that is somewhat a little abstract as of now, there is no compendium of resources like that, but you can definitely look up for different GitHub repositories, maybe. So, it basically depends on the aspect of biomedical that you're working on, right? Because there are multiple repositories specifically devoted towards dental imaging or specifically devoted towards brain tumor imaging, so you can find those repositories automatically at your convenience on GitHub. So what if you could suggest, if you could tell me the particular domain that you're interested in, I could help you out maybe more. Also, if you work on PyTorch, then I would definitely suggest you to refer to Monai once, because Monai is a really interesting imaging for the functionality that you could use specifically when you're working on medical imaging. So if you're familiar with PyTorch, you can definitely work with Monai. uh,
Yes, yes. I work with PyTorch, Keras, and TensorFlow, all of them.
got it, got
Um,
it.
Especially, in terms of like, for example, I've done a lot of deep learning with like computer vision, but then we didn't really have to work with image enhancement and all because we already get images that are pretty good.
Yeah,
So we didn't have to work so hard. At least they were not as blurry as the ones that you would at least put up.
yeah,
And there's not so much of information that you need to really get out of stuff.
yeah,
So it's pretty straightforward. So in terms of like pre-processing techniques, image pre-processing techniques,
yeah, yeah,
especially
yeah.
yeah, if there's something like that, because again the rest classification and everything I feel is similar to any other like regular deep learning that we do with images, any kind of image. So please correct me if I'm wrong though, because
No,
I'm
no,
just
no,
starting out.
no, no. You're absolutely right, because usually we do get good quality images, and we usually refer to just the pre-processing pipeline for image enhancement as well. So if you're looking for more resources on that,
Hmm.
I think there is a book I can refer to. Just one moment.
Yeah, please.
Uh, I don't think I have the link for it. I can just give you the
Yeah,
name.
the name. Yeah. All right.
Yeah, this is a
Thank you
really
so
great
much.
book. I referred to it, and it's really interesting.
Thank you so much, Sanya. Thanks a lot.
No problem. Any queries? The link to join the core channel is in the chat box. You can please refer to it and join the core channel where we'll be sharing all the resources. Also, if you're interested in Kaggle competitions, like I mentioned towards the beginning of the session as well, we have a Kaggle competition coming up, brought to you specifically by Cord AI, and it starts on January 27th. So please stay tuned for that as well. Thank you.
Thanks for the heads up, Sanya.
No problem. Are there any more queries? Okay, thank you everyone for joining. I think there are no more queries right now. You can connect with me on LinkedIn. I'll just put in my uh, link, connection link right over here. Uh, of late, I see a lot of work going on in biomedical text with NLP and GraphML. Yeah, that's true. That's true. A lot of work is being done on biomedical text, especially specifically when it comes on sentiment analysis, or when it comes on basically diagnosing the type of disease using health bots as well. I don't work on NLP or with graphs. I only work in computer vision, but that's a really great heads up. Thank you, Yashwant. Okay,
All
thank you,
right.
everyone.
Thanks, folks. Thank you, Sanya. That was a great and informative session. And we'll be putting up the resources on the CORD website, on our Slack channel, and maybe on the YouTube as well, where we'll share the current recording. So thank
Sure.
you, everyone, for joining.
Thank you.